everybody have a good day. And I'm Nick Mihailovsky, CEO of Enter Labs, and I'm happy to see you everybody attending our webinar on neural networks. And before we start with our today's topic, let me briefly announce what's happening in the few next weeks. Next week, we have Alexander Petushko near Mountain View, California, USA, talking about certified robustness, fundamentals, and challenges. On January 31st, Dmitry Chklovsky with the topic that has yet to be rectified, and the next week, that's probably February 7th, me myself with the talk about small language models and language model ensembles. And what's next, I don't yet know. And I'm happy to see today Tulika Bosset in Riyadh, France, and she'll be talking today and discussing detection of abusive language, mostly by domain transfer, I believe. So, Tulika, please welcome.
Sure. Thank you, Nikolai, for this introduction. I'll try share my screen now. So I hope you can see my screen.
Yeah.
Okay, great.
So before you start, what's the best time to ask you questions? As you go on, or at certain points, or at the end?
I think you can, so I have my presentation divided into 4 parts. So when one part ends, you can ask questions, I would be happy to answer. Or if you have like something that should come up at the end, I would be happy to answer at the end as well.
Okay, perfect. Then I'll try to moderate the questions so they are coming at your talk parts.
Okay, sure. Thank you very much. So hello, everyone. Thank you for being a part of this talk. I'm Tulika Bose. I'm a PhD student at the INRIA Lauria Labs and the University of Lorraine in France. And I'm supervised by Dr. Irina Elina and Dr. Dominic Four. And this talk is about my work that I did during my PhD in the last 3 years that I'm about to defend in the end of this month. And my work is titled Transfer Learning for Abusive Language Detection. So we know that social media in some form or the other has become an integral part of our lives. And with the ever-increasing reach of these platforms and the number of users, it has become a fertile ground for abusive language. The intensity of this problem can be gauged from the fact that based on a survey on US adults, it has been found that around 40% of online users have been victims of abuse at some point. And the intensity or the severity of abuse has increased over the recent years. Now, abusive language can take up several forms. And different terms have been used in the literature to indicate abusive language. So we use the phrase abusive language as an umbrella term to refer to all sort of harmful content present in the social media comments. Now, it is worth mentioning that hate speech is a particular kind of abusive language, which includes other forms such as personal attacks, derogatory language, general profanity, toxicity, etc. So why hate speech is different is that it targets a social group based on common societal characteristics such as race, religion, gender, etc. So it means that even if a hate speech is targeted towards an individual, it intends to insult that entire social group that the individual is a part of. So for example, the first comment here is actually an abusive language, but not really hate speech. But the second comment insults the entire group of women, and therefore it is hate speech. So in order to have a safe online environment, it is important to moderate the user-generated content for abusive language. And therefore, social media companies recruit several manual moderators to filter out these content or moderate these content based on the guidelines laid down by these companies. However, manual moderation is extremely time consuming. It involves huge cost, and most importantly, it results in a huge psychological toll on the moderators. So automatic detection of abusive language using natural language processing techniques can be of great help and can reduce the effort and the search space of manual moderators. Now, the problem with user-generated content is that it keeps varying over time. In particular, it has been observed that the state-of-the-art abusive language detection models they give decent levels of performance when they are trained on the same corpus and they are evaluated on the same corpus having the same distribution. However, the performance drops significantly when they are evaluated on a different corpus having a different distribution. So this domain shift occurs due to several factors, such as varying vocabulary, writing style of the comments, the different topics of discussions, or the different targets of hate, and other kind of shifts. Also, the sampling strategy that is used to collect this abusive language can result in spurious correlations due to the disproportionate presence of terms across classes. And this can result in the classifiers focusing more on domain-specific content rather than the domain-invariant content. And this results in poor cross-corpus performance. Now, at the same time, annotating a new hate speech resource every time it's costly and involves considerable effort. So in our work, we intend to perform cross-corpus classification of abusive language using binary labels of either abuse and non-abuse or hate and non-hate on social media text. And throughout this work, we have used deep neural network-based models. Now, our central goal is to transfer knowledge across corpora such that the adverse effect of domain shift is minimized, and also the annotation effort required in the new corpus for achieving decent levels of performance is reduced considerably. So now, what is transfer learning? So transfer learning is a concept that is used in machine learning where knowledge acquired previously from one domain or task is applied to solve a problem in a different but related domain or task. So in our case, the domain remains the same. The task remains the same, but we intend to perform adaptation across different domains. So this work is divided into 4 parts, and we try to explore answers to 4 different research questions. The first research question is, how do the topic memberships of target corpus comments with respect to the topics in the source corpus contribute to the generalizability of a classifier? Secondly, how do the domain adaptation methods from other tasks like sentiment classification perform for cross-corpus abusive language detection? The third question concerns how to reduce the corpus-specific bias for improving cross-corpus performance. And finally, how to effectively transfer knowledge from a resource-rich source corpus to a low-resource target corpus across varied online platforms. So in our work, we have used 5 different publicly available corpora that comes from different online platforms and have different class distributions. Davidson, Hateval, and Wasim are abusive language corpora that are sampled from Twitter. Dynamic is a dynamically generated corpus using a human and model in the loop process over the Dynamedge platform. And Ethos is sampled from YouTube and Reddit. Now, for Dynamic, actually 2 versions of these corpora was released, which has got some slight modifications. So we indicate these by version 1 and version 2. Now, in order to perform cross-corpus classification, we should have uniform number of classes. So we mapped all the classes that had harmful content, for example, hate speech or offensive, into a single class of abuse or hate. And likewise, all the neutral classes were mapped into a single class of non-abuse or non-hate. Now, these different corpora have got a different percentage of abuse, and the most imbalanced one is Davidson and Wasim here. Now, I'll start with the first research question, which is, how do the topic memberships of target corpus comments with respect to the topics in the source corpus contribute to the generalizability of a classifier. So in this case, we assume that we do not have access to any amount of data from the target corpus during training. So now the first question that arises is, why do we consider topic models in the first place? So topic models have the advantage that they can discover latent semantic structures from data without requiring annotations. Moreover, it can infer topic mixtures from unseen samples. In the past, topic models have been used for performing generic cross-domain text classification. So in our work, we investigate whether combining the topic representations with contextual representations obtained from state-of-the-art transformer-based models can help in improving generalizability. So for this, we incorporated a topic model called topically driven neural language model. Now, in comparison to traditional models, the topic models that can use pre-trained knowledge as an external knowledge is more suited to short social media text. So this topic model basically takes as an input a comment, and then it converts it to a comment embedding. So the original TDLM model actually used pre-trained BERT embeddings and applied convolutional neural networks over these pre-trained embeddings to compute this comment embedding. But it has been shown that sentence embeddings, that is directly generated from sentence encoders, pre-trained sentence encoders, are better at transfer tasks than word embeddings. So we slightly modify this model, and instead of using CNNs over pre-trained word embeddings, we use the universal sentence encoder model to directly generate this comment embedding. Now, this model actually uses an attention mechanism to associate these comment embeddings with different topic vectors and computes a weighted mean of the topic vectors, and then from this weighted mean predicts the different words in the comment. We use these weights as our topic representation or topic distribution for each comment. So that is indicated by TC. Now, as a first baseline, we use this TC, the topic distribution that we obtain, and we pass it through a fully connected layer and apply a classifier on it, and we train it. As a second baseline, we obtain representations from a model called HateBird. So it is a BERT model that has been retrained over large-scale abusive language corpus from Reddit using the mass language model objective. Now we extract the CLS token representation from this HateBird model, and then we pass it through another fully connected layer, and then we apply a classifier on it. Now, as a third model, which is the combined model, we combine these transformed representations, and then we pass it through another fully connected layer, and then we apply a classifier on it. So our intention is to see whether combining these two representations can be better at generalizability in comparison to the individual models. So moving over to the results, first, what we can observe is that the cross-corpus performance drops significantly on an average compared to the in-corpus performance. So for example, the HateBird model across corpora gave an average performance of 60 macro-F1 score, while on in-corpus it gave an average macro-F1 of 77.9. Secondly, we use a random vector as an ablation study. We combined a random vector having the same dimension as the topic models, and then we combined it with the HateBird representations. As expected, the average performance dropped in comparison to the HateBird representations. But while the topic models alone gave poor performance, when they were combined with the contextual representation, they actually resulted in improving the performance in 5 out of 6 cases and gave the best performance in 4 cases. Even in the last case where the performance did not improve, it actually retained the performance obtained from the HateBird representations. Now, moving over to a qualitative analysis, here there are 2 abusive comments from the target corpus of Davidson. These comments are associated with different topics in the source. So the first comment from Wasim to Davidson, it's a comment from Davidson. We can see that this comment deals with the topic of women and cooking. And it found associations with the topics 4 and 12 from the source corpus. So let's see what these topics are. Now, from the source corpus of Wasim and from the top words obtained from these 2 topics, we can see that topic 4 deals with sexism in sports, And topic 12 deals with a cooking reality show called MKR and its women participants. Now, secondly, the second comment actually deals with homosexuality, and it found associations with the topics of 3 and 7 from the source corpus of hate eval. Now, moving over to the last table here, we can see that topics 3 and 7 from the source corpus of hate eval actually deal with explicit abuse. So what does it say? So we can observe that these comments, so yeah, I forgot to mention that these are the comments that actually got misclassified by the hate-bot model alone, but got correctly classified either by the combined model or by the individual topic model. So these got correctly classified, most likely because the comments found associations with the abusive topics in the source corpus, and this provided a complementary information in addition to the information obtained from the contextual representations. So in conclusion, we have seen that models generally degrade in cross-corpus settings as compared to in-corpus evaluations. Topic models have the advantage that they allow the target corpus comments to trigger the abusive language topics from the source corpus. While topic representations themselves alone tend to lose the complete contextual meaning of a comment, combining them with contextual representations have been seen to improve generalizability in this task. So here I end my first part, and if there are some questions, I'll be happy to answer it, and otherwise I'll move on with the second part.
Yeah, Tulika, thank you. We have Q&A, we have chat, so please, everybody, feel free to ask questions. But if you don't have any, we'll go on to proceed. Yeah, let's go on to proceed and see if more questions will come later.
Okay, sure. Yeah. So now we'll explore answers to our second research questions, which is how do the domain adaptation methods from other tasks like sentiment classification perform for cross-corpus abusive language detection? So essentially, we try to explore whether the problem of domain adaptation in this task can be trivially solved by the existing methods that are already being proposed in the other tasks. So in this case, we assume, in this part, we actually assume that we have some amount of data from the target corpus, but we do not have labels associated with them. So for this, we explore unsupervised domain adaptation as it does not require annotations from the target corpus. Now, because annotating involves substantial time and effort, particularly in this task, so if the domain adaptation performs well, they can prove to be very advantageous. Basically, the aim of these domain adaptation methods is to align the source and the target representations in such a way that the classifier which is trained on the source corpus can perform quite well on the target corpus. Now, because sentiment classification has a rich literature of domain adaptation approaches, so we investigate two popular approaches from sentiment classification, which are the pivot-based approaches and the domain adversarial approaches. So in the case of pivot-based approaches, we use one approach called pivot-based language modeling and the second pivot-based encoder representation of language, or PERL. So what are pivots? So pivots are common shared features which follow two properties. The first one is that they should be frequently present across the source and target corpora. And the second property is that they should be highly correlated with the source labels. Now, once these pivots are extracted, these methods use other terms in the corpora to predict these pivots. And in doing so, it extracts common representations from the source and the target. Now, for domain adversarial approaches, we explored two approaches. The first one is hierarchical attention transfer network, which is HATN. And the second one is adversarial adaptation with distillation, or AAD. So domain adversarial approaches use this adversarial objective to produce domain invariant representations across from the source and the target. Now, in addition to this, we also investigated another adaptation approach where we fine-tuned the hate-bot model on the unlabeled content from the target using the masked language model objective. And then subsequently, we fine-tuned it on the source corpus using the labels. Now, we intend to see the results of what happens. Unexpectedly, we can see from this last row that the average performance of all the domain adaptation approaches from sentiment classification had a very poor score compared to the no adaptation case. However, when the Hateport model was adapted on the target corpus, it gave improvements in most of the cases. Now we should investigate why this happens. So I would start by investigating the pivot-based approaches. So pivots are actually domain shared features across the source and the target corpora. And ideally, they should exhibit the same behavior because they serve as bridge across the domains. So for this, we compute a ratio of the number of abusive comments that has a particular pivot PI divided by the number of non-abusive comments with that particular pivot PI. And we compute this ratio both for the source and the target. So this ratio basically answers the question that if a pivot has higher affinity towards one class in the source corpus, does it also have higher affinity towards the same class in the target corpus? Now, in an ideal scenario, both these ratios, RIS and RIT, should be either less than 1 or they should be greater than 1. Now, TH is a threshold that ensures that the ratios are far away from 1. Now, in an ideal scenario, if the domain adaptation performs well, we would expect that a higher percentage of the pivots satisfy this ideal condition. So let's see what these percentages are. What are these percentages? Now, unfortunately, for the threshold of 0.3, we can see that the percentages are not quite high. In the worst case of Wasim to Davidson, we obtained a low percentage of 18.8, and for the best case, we obtained a percentage of 15.1.4, which is still quite low. This means that the remaining amount of pivots did not capture the shared features optimally, which means that they had correlations towards opposite classes in the source and the target. And this most likely happens because of the complexity of the abusive language detection task. It is difficult to find n-gram pivots whose meaning and behavior remains unchanged across corpora. Now, for the domain adversarial approaches, for the worst case of Wasim to Davidson, we visualize the source and the target representations obtained after adaptation using PCA plots. We can see that with HATN, in the first place, the source representations themselves lose their discriminative power, and therefore the target representations cannot be classified properly. This happens because HATN learns a joint objective during adaptation where it updates both the source encoder and the target encoder. And because of this joint objective of adversarial adaptation plus the classification loss, it is possible that it might mess up the source representations too. On the other hand, in AAD, the source encoder is kept frozen during adaptation, and therefore the source representations are well separated into the two classes. However, the target representations are still quite messy, and it does not follow the class separation exhibited by the source representations. For the best case of hate eval to Davidson, we can see that now in this case, HATN, for HATN, the source representations are quite well separated into the two classes, and the target representations are also separated, and it follows the class separation exhibited by the source representations. And this is a good point. On the other hand, in AAD, while the source representations are still well separated, the target representations are quite mixed. And this is reflected in the higher macroFM score from HATN compared to AAD. Now, one limitation of this approach, of the domain adversarial approaches like these, are that it aligns the distributions from the source and the target without considering the class boundary information. So while the marginal distributions align, the class conditional distributions does not align. And this is a problem for our task. So now in conclusion, we have seen that existing unsupervised domain adaptation approaches are quite suboptimal for the task of cross-corpus abusive language detection. While pivot-based pivot extraction methods were unable to capture the shared space optimally, The class boundaries learned by the adversarial methods do not typically generalize well to the target. On the other hand, we have seen that the MLM fine-tuning on the target corpus improves the adaptation. So these pivot extraction methods should ideally account for the higher level semantics of abusive language, and the adversarial methods should perform class conditional alignment for better adaptation. So here I conclude the second part, and if there are questions, I would be happy to answer them. Otherwise, I'll move on to the third part.
Yeah, please, any questions, Q&A, chat? Okay, let's go on.
Okay, great. Now, moving over to the third research question, how to reduce the corpus-specific bias for improving cross-corpus performance in hate speech. Now, in this part and the next part, we will specifically focus on hate speech, because hate speech is targeted against minority groups, and therefore it is more concerning. And also in this part, we assume that in addition to the unlabeled content from the target, we have some access to the validation set from the target corpus. So now, due to the biased distribution of certain terms across classes in hate speech or hate speech corpora, some terms might be associated with one class more predominantly compared to the other class, even without being useful for the task. And this kind of correlations is called spurious correlations. And because of this corpus-specific bias, classifiers tend to learn more from the domain-specific features rather than the domain-invariant features. And this results in poor cross-corpus performance. So here are two examples from a target corpus. These two comments, genocide is never okay and women are goddesses, are actually non-hateful, but a model that was trained on a different source corpus misclassified these instances as hateful because it learned some spurious correlations between the word genocide and women and the hate label. So in order to identify and penalize these spurious correlations, we explore in this work whether model explanations can help us. Now, feature attributions are a class of post hoc model explanations that assigns attribution scores to individual terms in the input comment based on how important they were for the prediction. For example, here is a comment, immigrants are helpful, and this is actually a non-hateful comment, but the a model actually predicted it as hateful wrongly. And why this happens is because a higher attribution score was assigned to the term immigrants, so the model was biased towards this word, and therefore it misclassified it as hateful. Now, the prior works, in order to reduce this corpus-specific bias, they have penalized the attributions of a manually predefined list of terms called group identifiers. These are the terms which represent social groups that are common targets of hate. For example, Muslims, Jews, Blacks, etc. However, there are three shortcomings of these approaches. The first one is non-exhaustiveness, which means that a manually curated list may not involve all sorts of group identifiers. Secondly, reduced coverage, which means that the terms that cause spurious correlations may not always be group identifiers. They could be other terms as well. And thirdly, we know that in social media, new terms keep emerging frequently. For example, terms like COVIDiot and finfluencer that evolved in last few years. And a manually predefined static list cannot take into account these terms. So we need an automated approach to extract and penalize these spurious correlations without relying on a predefined manually curated list. So for this, we propose two domain adaptation approaches. And these approaches follow a process called dynamic model refinement, or DREF, and hence we call these two approaches DREF1 and DREF2. So in the first approach, we use the misclassifications on a small amount of labeled data from the target to identify the spurious correlations that is learned by the source model. In this case, we extract the terms that are essentially common across source and target, but are correlated to the labels in the opposite way. In the second approach, we intend to penalize corpus-specific terms in the source corpus that are also simultaneously highly correlated to the labels. And because of these corpus-specific terms, the models focus more on these specific content rather than learning from the wider domain invariant content in the comments. And in this case, we extract the terms that are specific to the source corpus, unlike DREF1. So now moving over to DREF1, in the first step, we train the BERT model on the source label training set. And we do this for every epoch. We extract a ranked list of terms from the corpus, from the source corpus, that has higher attributions towards the class hate and non-hate. So we intend to extract two different lists. For this, we use the instance level, the local feature attributions. So for instance, for a term present in all the hateful comments, we compute an average of their local feature attributions to find the corpus level global attributions. And likewise, we obtain the global corpus level attribution score for the same term for the non-hateful class. So at the end, we have a list of terms for both for the hate class and the non-hate class, which is global and at the corpus level. And we sort these terms in a descending order based on the attribution score assigned to the term. So higher the score, it is assigned to the topmost level in the list. And we do this, we repeat this procedure across every epoch. Now, in the second step, what we do is we identify the misclassified instances in the target corpus. That means the false positives and the false negatives. And then using the instance level attribution scores in those misclassified examples, we extract the top K terms that have higher attributions towards the misclassifications. This means that these top K terms were actually instrumental for resulting in these misclassifications. Now, once we have this list, in step 3, we filter out the set of terms that also caused correct classification in addition to misclassification. And then along with this, we take the terms that are common to this list from the target and the terms that were also present in the globally ranked list, GL hate and GL non-hate, where we extract the top N terms from this source list. So now we extract terms by doing an intersection between these two lists. Now, this final list is called SEPI because it keeps updating after every epoch. And these are the terms that are likely to cause spurious correlations. And therefore, we intend to penalize the importance assigned by the model to these terms. So for penalizing these extracted terms, we follow 3 different strategies. So in the first strategy, we simply mask out these terms. Sorry for this error here. We mask out the terms present in this list, and then we train the model in the next epoch. In the second strategy, which is called REG, we add an additional loss objective to the original classification loss, and this objective is called attribution loss. So what it essentially does is it applies an L2 norm over this attribution scores such that the model penalizes the attributions or importance assigned to these terms. Now, in the third strategy, it is same as REG, but in this case, we combine the predefined list of terms that is manually curated along with the automatically generated list of terms at the end of every epoch using DREF1. So that ends the process of DREF1. And now for DREF2, in the first step, what we do is basically here we intend to extract the corpus specific terms from the source corpus, which also have higher attributions towards the labels of hate and non-hate. So for this piece, even before training the BERT model, we use a domain classification step, which is basically a simple logistic regression model because it is inherently interpretable. We use this classifier to identify whether an instance comes from the source or it comes from the target. And while doing so, we can extract the terms that are predominant in the source corpus by using the logistic regression coefficients, we can extract these top M terms that are important for identifying the source domain. And we call these terms SLR. In the next step, what we do is, in this case, since we have access to the unlabeled data from the target, we start the training with a masked language model-based adaptation on the target corpus. And after this adaptation, we start with the supervised training. And at the end of every epoch, we obtain this global list of GL hate and GL non-hate, which is same as which follows the same procedure as I explained before. And once this list is obtained, in the third step, we take an intersection of the terms present in the first list, which was obtained from domain classification, which is SLR, and this second list, where we extract the top N- terms from this list GL hate and GL non-hate. And now we can hypothesize that the intersection of these terms are the terms that actually cause spurious correlations, and these are the terms that are actually corpus specific. So in this case, we penalize the importance assigned to these terms using the two strategies, reg and com, as I had mentioned before. So we used three different feature attributions in our approaches for our experiments. The first attribution method is called scaled attention, where we scale the attention weight associated with every term with its gradient. The second attribution method is called integrated gradient. So what basically it does is it computes an integration of the gradients across a straight line path from the reference input towards the actual input. And in our case, we used the zero embedding vector as our reference input. Now, the third feature attribution method is deep learning important features, or deep lift. So given a set of neurons that are necessary and sufficient to compute the target output neuron T, it assigns contribution scores C such that the difference from reference in the target output neuron, which is given by delta T, is attributed to the sum of the difference from reference in Xi, which is our input. I'll not go into the details of these attribution approaches because it will take a lot of time. I can answer questions later if required. Now, moving over to the results, with DREF1, here we do not have access to the unlabeled content from the target. We can see that on an average, all the penalization strategies improve the performance compared to the two baselines. The first baseline is the vanilla baseline, where the model was trained on the source corpus and was evaluated on the target corpus. And the second baseline is where we only use the static list of predefined terms and penalize them. We can see that in most of the cases, the strategies of reg and com gave improvements compared to the vanilla baseline, while the improvements were quite inconsistent in the case of predef, and on an average, there was no improvement for predef. Secondly, these are the results for DREF2 with deep lift, where we have access to the unlabeled content from the target corpus. Since we have access to the unlabeled content, we compare it with the vanilla baseline where we use the masked language model objective to adapt the BERT model on the target corpus. Along with that, we also compared it with the domain adaptation approaches of Pearl and AAT that I had described in the previous part. So here we can see that the average score obtained by both the penalization strategies are quite similar, and it has improved over all the baselines. Moreover, there are improvements in the individual cases as well. On the other hand, the domain adaptation approaches improve the scores only in a single case. Now, moving over to a more qualitative analysis. Here there are two non-hate examples from the target corpus, and a vanilla model, a vanilla BERT model actually classified these non-hate examples as hate. And this happened because of higher attributions assigned to the terms, which are slur terms. And because of the presence of these slur terms, these two comments are actually misclassified as being hateful. However, after refining the model using DREF1, the model looked into the wider context. It saw that the subject of these comments were wildlife and NHS, and therefore it was correctly classified as non-hateful. In case of DREF2, here is an example of hateful comment, which is, it is good to talk to your wife, but it is easier to say shut up and make me a sandwich, not sexist. This comment was actually misclassified as non-hateful by the vanilla model. However, with the refinement, the model looked into the wider context and it gave higher attributions to terms like wife, shut, make me a sandwich, not sexist, and therefore it correctly classified this comment as hateful. So in conclusion, we proposed two domain adaptation approaches, which followed a scheme of dynamic refinement to reduce the corpus-specific bias. We could increase the coverage because of this automatic extraction compared to the predefined list of terms. And we can see, we saw that different types of terms are penalized in the two approaches. In the first approach, we penalized the terms that were common to the source and target, but had different behavior. And in the second approach, we penalized the terms that were specific to the source corpus, but were highly attributed to the hate and non-hate classes. And this penalization and refinement helped the classifiers to focus more on the wider domain invariant context of the comments rather than specific terms. So I conclude with the third part and I'll move with the fourth part. If there are some questions, I can answer those.
There are questions. First, Slav asks, there are cases where people might use lots of curse words to express their emotion without targeting a certain group of people. Do these cases can be handled by the model as well, or whether they will be classified as abuse or hate speech?
Okay, so in that case, it would be like that is also something that is supposed to be handled by this refinement approach, because this approach does not only identify whether a comment is hateful, but it also correctly identifies whether a comment is non-hateful. So by that, I mean that a vanilla model might pay a lot of attention to some slurred words, even if the slurred word is actually used in a very friendly sense. And this is actually what is meant by corpus-specific bias or spurious correlations. So if this approach can work, if this approach works properly, and if there's sufficient evidence, in that case, it will force the model to not pay attention to those slur words, but rather look into the domain invariant content or the wider context of the comments and see whether this was used in a friendly sense or it was actually used to target some social group. Yeah.
Okay, thank you. I also have a question. The question is there any specific reason you work with words versus working with embeddings? What I mean, embeddings typically represent some chunks of space that are specifically specific to certain concepts or some concepts, space parts, and so on. And theoretically, working with embeddings, not with specific words, would allow for some extra generalizability. Or is there specific evidence that words do work better than embeddings here?
Okay, so here we do not directly use words. So here also we are using the embedding space. So basically we are using the embeddings that are generated by the BERT model. So when this approach actually works in practice, it uses the embeddings. Here I have shown words to where I have mapped those embedding spaces to the individual words. But ultimately the model works in the embedding space itself. So when these feature attribution methods are computed, like the attention multiplied by the gradient of attention or the integrated gradients, all of them work at the embedding space. So they use the contextual embeddings that are computed by the BERT model, and they try to find out whether higher importance is given to a particular word piece token, which has been mapped to the embedding space. Also, the other thing is we use feature attributions, which means we use the scores to the individual terms or the word piece tokens rather than an abstract concept. So that is one shortcoming, and this approach actually can be improved by not just using the feature attributions, but also using other forms of explainability methods. One of these is testing concept activation vector, which has the advantage that it can use an abstract concept, for example, abuse against a particular target group, which is an abstract concept, and it can find how sensitive the model is towards that abstract concept. But here in this case, we have worked with the embedding space only, not directly with the words. I hope that answers your question.
Yeah, thank you. Let's go on.
Okay, sure. Yeah. So finally, I move on to the last question here. How to effectively transfer knowledge from a resource-rich source corpus to a low-resource target corpus across varied online platforms. Here, we assume access to a small amount of label data from the target that we also use during our training. So a common approach for transferring knowledge is sequential transfer, where the model is first trained on the source corpus, and then it is subsequently trained on the target corpus. But one limitation of this approach is that it is not systematic, which means while learning this transfer, the relationship between the source instances and the target instances are not really considered to decide the amount of transfer. Now, recently, a neighborhood framework for transferring knowledge across domains have been proposed, which is called KNN+. Here the neighbors are actually extracted from a pre-trained sentence encoder, which models the similarity of the sentences. So what it does is, for every target instance, it extracts its neighbors from the source corpus, and it models the amount of transfer using a neighborhood agreement, which says that if the neighbor from the source and the instance from the target have the same labels, there should be higher transfer compared with the neighbors that have opposite labels to the target instances. And this is called label agreement. But one limitation with this approach is that it does not consider that different neighbors can actually have different distances with the target instance based on the cosine similarity or the distance in the embedding space. So this approach does not consider these varying levels of proximity of these neighbors. And ideally, both these varying level of proximity along with label agreement should be considered while deciding the amount of transfer. So in our work, we jointly model the similarity of neighbors in a sentence embedding space along with their label consistency to decide how much transfer should be done from the source instance to the target instance. And this kind of optimization problem can be efficiently solved using optimal transport. So because it can find correspondences between source and target instances in a using the geometry of the underlying embedding space. Okay, so optimal transport is a theory that can compare two probability distributions in a geometrically sound manner. So in our work, we used the framework of joint distribution optimal transport, or J-dot, which has been introduced for domain adaptation. So let's say we have two empirical distributions, mu-s and mu-t, defined on the product space of Z cross Y, where Z is the embedding space through a mapping function G, and Y is the label space. Now, the balanced optimal transport formulation, which is given by OTB, actually seeks for a transport plan gamma in the space of probability distribution, a joint probability distribution, pi mu-s mu-t, and it also applies a marginal constraint on this pi mu-s mu-t, such that the marginals of this joint distributions are actually mu-s and mu-t. So what this marginal constraint means is that all the mass from mu-s should be transported to mu-t, and there should not be a loss or creation of mass in the process. Now, this transport optimization problem actually tries to minimize this transport plan gamma in such a way that the cost of transfer from mu-s to mu-t is reduced where the cost of transfer is given by Cij corresponding to the ith source instance and the jth target instance. However, when there are outliers in the data, this marginal constraint can result in additional transport cost because it can force the transport plan to transport the outliers as well in order to maintain this constraint. So now this marginal constraint can be relaxed using another formulation of optimal transport called the unbalanced optimal transport. So this formulation actually is robust to outliers and can result in creation or destruction of mass. So here, the first term here is the entropic regularization term, which ensures fast computation of optimal transport distances. And the second term here is the Kullback-Leibler divergence term. And this is the term that allows relaxation of the marginal constraint. Okay, so the cost matrix that we saw previously in this J-dot framework is given by a weighted combination of two distances. The first one is the embedding distance, which is the distance in the embedding space between the ith source instance and the jth target instance. And the second is the label consistency loss. Basically, it's a cross entropy loss that enforces a match between the labels of the ith source and the jth target. Also, because we deal with this high dimensional embedding space, in order to make the computation of optimal transport losses feasible, this optimal transport plan can be computed at the level of a mini batch, which is given by M. So now we can use this sentence PERT space to extract k nearest neighbors of every target instance using this GS-PERT mapping, which maps the input to the sentence PERT space. Now, for computation of this optimal transport plan gamma, we can use the distances in the S-PERT space actually. And what it will do is it results in learning gamma in such a way that it allows higher transfer whenever a source and the target instance are closer in the S-PERT space and simultaneously they share the same label. So we end up with this final optimal transport formulation that we propose, which is an unbalanced formulation using this nearest neighborhood information. Along with the losses that I mentioned before, we add two additional cross entropy loss, one for the source and the other for the target, because we need these for the classification task. And these cross entropy losses are weighted by theta s and theta t, respectively. So now this optimization problem can be solved in 2 steps. So this is a 2-step training procedure. In the first step, we fix the model parameters. So essentially, we use a BERT model, but we fix the parameters of the BERT model, and we first try to compute the optimal gamma. And these steps are actually repeated in every iteration. So for computing the optimal gamma, as I mentioned before, we use the S-BERT space in the cost matrix. And here in the cost matrix, the entries that correspond to non-neighbors given a k nearest neighborhood space of from the source for every target, we explicitly assign a maximum value. So this ensures that no transfer should happen between non-neighbors. So we use an optimal transport solver to find the solution of the optimal gamma for that iteration. And once this optimal gamma is computed, we fix this gamma. And now we update the parameters of the BERT model for the BERT encoder G and the classifier F. In this case, for computing the label consistency loss, we use the predictions of this from the source model and the actual labels from the target. In this case, we do not use the sentence BERT space because what we actually do is we transfer the neighborhood information from the sentence BERT space into the BERT space indirectly using this computed gamma. And this ensures that the BERT embeddings are learned in such a way that 2 sentences, one from the source and the other from the target, come closer to each other if they are similar in meaning and also share the same label. So now we experiment with 4 different variants of this approach. The first one is called OTUNN, which is the classic approach, the baseline approach in our case. In this case, we do not use the source cross-entropy loss. In the second approach, which is OTUNN pre-select, we first, even before starting the training, we pre-select k nearest neighbors from the source for every target instance, and then we start the training. So in this case also, we do not use the source cross-entropy loss and assign a weight of 0 to that cross-entropy loss. In the third variant, which is OTUNN plus S loss, it is the same as the first variant, but we add this additional source cross-entropy loss by giving it a weight of 1. The fourth variant, which is OTUNN pre-select plus S loss, it is similar to the second variant, but in this case, we use the source cross-entropy loss. And for all these variants, we give a weight of 10 to the target cross-entropy loss. This is given a higher weight because our ultimate goal is to learn the classification in the low resource target corpus instead of the source. So here are the results. For this, we have assumed that we only have access to 400 training instances from the target and 100 validation instances. So the first row is for target FT, which means that here the model is only trained on the low resource target corpus. And we can see that in general, transferring knowledge from the source corpus to the target has helped in improving the score. Now, sec-FT is actually the sequential transfer. Yes, I can see a hand raised. Do you have a question?
I believe we can go on and answer the questions when your part is done.
Okay, yeah, sure. Okay, so the first sec-FT is sequential transfer. Mixed FT is an approach where we extract M training instances, we sample M training instances from the source and also from the target, and then we update the model based on this joint cross-entropy loss of the source and target. KNN plus is the neighborhood framework that I described previously, which uses label agreement. Now we can see that in most of the cases, the best performances are obtained using the optimal transport, the OTUNN variants. Also, the performances are significantly improved in most of the cases compared to the baseline of sec-FT. Whereas for mixed FT and KNN plus, the results are more or less inconsistent. Also, another interesting observation is that compared to OTU, which is the optimal transport formulation without having nearest neighborhood information, the OTUNN variants have improved the performance. And this means that the neighborhood information has helped in better optimization and better learning of what we intend to learn here. So now we can vary the sizes of the training data that is available from the target. We can see that in both the cases, the last bar, which is the performance given by the OTUNN variant, is consistently high compared to the baselines of target FT and mixed FT. Mixed FT, on the other hand, is quite inconsistent and in some cases actually result in a drop of performance. Also, we can see that the improvements with the OTUNN variants are higher when the amount of label data that is available from the target is low. Now, for a qualitative analysis, what we can do is after the OTUNN framework has been learned, we can extract the k nearest neighbors for a target instance from the source using these learned representations and compare these extracted neighbors with the neighbors extracted from a sentence bird space. So now we have a target hateful instance, which reads as, I am not sexist, but girls who smoke are a big turnoff. Even if you're supermodel status, it's a turnoff. So now the nearest neighbors, the top 5 nearest neighbors, which were extracted from the sentence bird model, also speak about women and smoking, but 3 out of these comments are actually non-hateful, while 2 of them are hateful. So if a KNN classifier is trained on these representations using a majority voting, the target instance will actually be misclassified as non-hateful. However, when the nearest neighbors are extracted from this learned OTUNN space, all the neighbors, the top 5 neighbors, are actually hateful, and they speak about women in a derogatory sense. So here, when a KNN classifier is applied on these learned representations, the majority voting would result in correctly classifying this target comment as hateful. Now, in order to verify that this actually happens in majority of the cases, we can do a quantitative evaluation. So here we do the same thing. We vary the number of neighbors and extract the top K neighbors from the learned OTUNN representations and compare the performance with the neighbors extracted from expert representation. And we do a majority voting of the labels. So here we can see that for different numbers of neighbors, OTUNN framework results in consistent improvement in performance. So in conclusion, we have proposed a framework for transferring knowledge to a low-resource hate speech corpus by incorporating neighborhood information with optimal transport. And this is a first work that introduced optimal transport to the hate speech detection task. Now, this allowed learning of the amount of transfer from the nearest neighbors based both on the proximity in the sentence embedding space as well as their label consistency. We saw that this resulted in substantial improvements across hate speech corpora in low resource scenarios. And our qualitative analysis demonstrated that the learned representations can embed both semantic as well as label similarities, unlike the sentence encoder representations. So overall, we have explored strategies that can effectively transfer knowledge across abusive language corpora amidst domain shift and in a way that the cost of the annotation effort required in the new corpus can be minimized considerably. We saw that topic representations provided complementary information to the contextual representations, and it helped in improving the generalizability. We also showed that the existing domain adaptation approaches from other tasks are not really suited to abusive language because of the complexity of this task, and they perform suboptimally. In order to reduce corpus-specific bias, we performed an automatic extraction and penalization of terms that can cause spurious correlations, and that resulted in improved cross-corpus adaptation. And finally, we also saw that transferring knowledge by jointly modeling the proximity of neighbors across corpus, along with their label similarities, helped in improving the performance in low-resource targets corpus scenarios. Overall, our study helped in a better understanding and improving the robustness and adaptivity of abusive language detection models. So with this, I conclude my talk, and thank you very much for listening. And now I'd be happy to answer your questions as well.
Thank you, Tulika. If there are any questions, Pavel, who have raised the hand, if you still want to ask a question, please do repeat that. And meanwhile, when you are getting the question, Tulika, can you get to the slide where you compare the optimal transport models?
Yeah, sure.
So when you do optimal transport, how do you do classification in the target domain?
Okay, so so I'll move to this architecture here. Mm-hmm. So in this case, while we are learning this joint objective, we also have this we are also learning a classifier here. And because we are learning the classifier, we can directly use this classifier for inference. So we are already learning how to assign labels to the instances. So this objective already includes a source cross entropy and the target cross entropy loss.
Okay. Yeah. So it's a cross entropy.
Yeah.
Have you tried classifications with KNN?
Yeah, exactly. So here, actually, I have not given all the baseline results, but we also tried like two flavors of KNN. First is the simple majority voting of KNN with expert, and the second is where we used a weighted voting based on the cosine similarities of the neighbors. So that gave poor performance because it was KNN classifiers not actually trained that way. So I did not include it here because in order to shorten the.
What I basically want to say is that optimal transport induces a new metric in the target space. And with a good metric, KNN classifiers typically exhibit very good performance, at least as good as cross-entropy loss and typically, not always, but in many cases, they have better performance than cross-entropy loss for classification cases where you have a good metric. And optimal transport introduces a new metric, new closeness metric in the target space. And if you measure closeness of sentences, of utterances using this metric, I would say you should get better classification results than you do with cross-entropy loss. If you have repeated and that didn't work, that's interesting. All this part is extremely interesting, of course. So did you use KNN in the target space using optimal transport induced metric, or did you do like a straightforward KNN?
Okay, so in the so I did not use KNN in the target space, basically because the target space only has very few examples. So always I have extracted neighbors from the source corpus. I did not consider the neighbors present in the target corpus. That is one thing.
When you have an optimal transport, you have images of the source sentences and source label in the target space. Am I correct?
Sorry, could you please repeat?
Yes. So we have two distributions. One in the source domain and one in the target domain. When we do optimal transport, we basically move the distribution from a source space to the target space. Is it correct?
Yeah.
Then we have every sentence in the source space has its image in the target space.
Yes, exactly.
And if we have images of the source domain in an aligned distributions in the target domain, we can do KNN classifier with that.
Okay. Yes, exactly. So that is exactly what I did here, where after this adaptation using OTUNN, where this source representations were transformed to the target representations space, then we used a KNN classifier. So here, this is a KNN classifier only. This is not the classifier using the cross entropy loss.
Yeah, do you have any comparison of the classification results using KNN here with those results using cross entropy loss?
Okay, I do not have a direct classification result here, but we can go back to the table before, and we can see whether there is a difference. Because the target in the amount of label data from the target was same in both the cases. So we can see the first case here, like it gave the maximum score that we got for 65.6. I think, sorry, dynamic to Wasim. It was 71.6. And I think it was, yeah. So here in this case, the result was, as far as I remember, and also evident here is through a KNN classifier, the performance is lower compared to training it end-to-end using cross-entropy. But it is possible that the KNN classifier might give a better score after this adaptation, but I did not find that the KNN classifier was actually giving better scores in comparison to this end-to-end training.
Okay, that's probably problem specific.
Yeah, that's true.
So it's interesting. Okay, we have, I believe, more questions. Okay, no more questions. It's accidental. Okay. Any more questions, colleagues? You have Q&A. We have chat. You can raise a hand. Meanwhile, I have yet another question of like a pretty general type. you work with domain adaptation, but a lot of the data sets you work with come from Twitter. And on a certain level, that's the same domain. So how, of course, that's different data sets collected by different research groups and so on. But how do you say that these domains are really different? Of course, that's a different data sets for sure. But how you say the different data sets are really different domains?
So first thing is we actually used data from other online platforms as well. So here, for example, this Vasim corpus is from Twitter. Ethos is not from Twitter. It is actually from a sample from YouTube and Reddit. And dynamic is not from Twitter or not from the other online platforms. It is actually a human and model in the loop generated data using Dynabench platform. So here we have, for this last part, we have actually used data from different online platforms. Now, secondly, even if we use data from the same online platform like Twitter, what we have found is these data sets are actually different in different contexts. For example, in one of the data set, there is a lot of abuse against women, like the targets of abuse was a particular social group, while in the other corpus, there were a lot of different targets. For example, in the dynamic corpus, abuse has been directed against other groups like religious or ethnic or particular to different countries like anti-Asian abuse. So the targets of abuse are different. That is one kind of difference. The other kind of difference is the language forms that have been used. So there is, it is relatively easy to find out whether a comment comes from the Vasim's corpus, looking at its language. So in Vasim's corpus, actually, most of the comments were created by two or a small subset of authors, and the language forms were quite specific to that particular corpus. But in other corpora, there could be a difference in the language forms. Also, like in sentiment classification, we can have domains of like airplane compared to, let's say, something else like radio or some other domain. Similarly, this change of context can occur even if we consider the corpus collected from Twitter. There could be a change of context. For example, in the Vasim's corpus, this abuse is directed in the context of women in sports or women driving cars or a cooking reality show. But in other corpora, there could be other contexts or other topics, such as in dynamic corpus, there is a wide variety of topics that are more general compared to the Vasim's corpus. So these topic distributions, the topics that are discussed across these corpora change, and all these factors actually result in a change of domain, even if the data is collected from the same platform. So I hope that answers your question. Okay,
let's say so. All right. I believe there are no more questions. Thank you, Tulika, for your report here. And I believe several interesting insights are there in your work. I really like the part about optimal transport and the insight that domain transfer requires transferring not only the distribution but also class boundaries is also important for me personally.
Yeah.
Okay. Thank you, and welcome to report your new works here. And thank you, everybody.
Surely, thank you very much. Thank you very much for the questions as well and for being here to attend the talk. Thanks a lot.